In this playlist, I'm showing you how to build a CPU. If you haven't watched the previous video, check out the link to the playlist.
Wanna watch?
Yeah, alright.
In the previous video, we learned how to create a NAND circuit using transistors. In this video, we want to move up a level of abstraction and talk about Boolean logic. Let's start by reviewing the basic Boolean operators. We already encountered the Boolean unary operators, including the identity function and the not function. Unary operators are operators, or functions, that have only one input. There are also binary Boolean functions, or operators, which use two inputs. The basic binary functions include AND, OR, and exclusive OR. Here are the truth tables for each of these functions. We can also combine operators to create compound Boolean operators. The NAND operator is a good example of a compound operator, which is composed of the AND operator followed by the NOT operator. As we mentioned, the NAND operator is the foundation of digital computation, which means we can build all other Boolean operators using the NAND function.
I want to work. I want to build something of my own.
When we are dealing with circuits that mimic Boolean functions, we refer to these circuits as gates. So, for example, we might refer to the NAND circuit as a NAND gate. Based on the NAND gate, we will develop a NOT gate, an AND gate, an OR gate, and an XOR gate. It would be tedious and error-prone to have to connect up the individual transistors and resistors every time we want to build a NAND gate. Plus, computers use millions of these gates, which would require a lot of space. If such were the case, you would need a forklift just to carry a cell phone around. Fortunately, electrical engineers have been able to shrink this technology down onto silicon chips, called integrated circuits, or ICs.
I see.
Where the transistors are literally microscopic. Because we can't see the parts on the chips, chip makers label the chips with identifying numbers. The chips we will use in this video are 7400 chips. The 7400 chips contain 4 NAND gates, as shown here. Each 7400 chip has 14 leads, 7 on each side. This dimple on the chip allows us to orient the chip so that we know which leads are which. Instead of this dimple, some chips indicate the first lead with a tiny circle in the chip just next to pin 1. We notice that in the diagram, all the pins have labels. These labels help us identify the pins with the appropriate behavior. For example, pins 1 and 2 are the inputs to the first NAND gate. Pin 3 is the output for the first NAND gate. Pins 4, 5, and 6 are the inputs and output respectively for the second NAND gate, etc. The diagram labels pin 7 as GND and pin 14 as VCC. These pins are the pins that power the chip. GND is an abbreviation for the word ground, which means that this pin should be connected to the negative side of the power source. VCC indicates the lead for the positive side of the power source. Let's investigate how these chips work by building a simple circuit that uses the chip. We begin by placing the 7400 chip so that it straddles the center gap of the breadboard with 7 pins on each side of the gap. Also, we place the 2 switches so that they straddle the gap. We plug one end of a 1K ohm resistor so that it connects to pin 3 of the 7400. We plug the other end of the resistor into an unused column of the breadboard. We plug the anode of the LED, which is the longer lead, into the same column as the second lead of the resistor so that the resistor is in series with the LED. This is to protect the LED as we discussed previously. Connect the other lead of the LED to an unused column. Also, connect the power source to the red and blue rails on the breadboard. Finally, use jumper wires to connect the rest of the circuit as shown in this schematic. You may want to pause the video here so you can take time to think about this circuit and why it does what it does. Once we connect and test this circuit, we see that it behaves exactly like the circuit we built in the previous video using transistors. These circuits are equivalent, but the chip creates a nice abstraction that allows us to forget about the details of the NAND gate and treat it as its own component.
Forget about it.
We have mentioned several times that we can use NAND gates to build all other Boolean operators. Now we are prepared to show how we do this. Let's start with building the NOT operator from a NAND gate. Remember, the NOT gate has one input and one output. If you're the kind of person that likes puzzles, you may want to pause the video here and see if you can figure out how to use a single NAND gate, along with other components like switches and resistors, to create a NOT circuit.
Hold on. Junior, pause the video.
One of the challenges with creating a NOT from a NAND is that the NAND has two inputs and the NOT only has one. This is a problem, but it is also a clue. If we look back at the truth table for the NAND function, we see that NAND only outputs false if both inputs are true. So what we probably need to do is replicate our one input for the NOT to both inputs for the NAND. In fact, if we tie both inputs of the NAND together, then when the input is false, the output is true, and when the input is true, the output is false. That is exactly what we want. Let's look at the circuit. If we build this circuit and test it, we see that when we push the button, the LED turns off, just like the previous NOT circuit we built with transistors. Why would we build this same circuit with a NAND gate instead of just using transistors? Well, while this may waste a transistor, it is very easy. What we have done here is we have moved up a level of abstraction. Now, instead of thinking about electronic components like resistors and transistors, we are thinking in terms of Boolean logic. Since we have moved up a level in our thinking, our diagrams should start to reflect this level of thinking. To do this, we don't draw electrical circuits like we have to this point. Instead, we will start using Boolean schematics. The Boolean schematics only show the logical connections. We ignore the details of the circuit like resistors and power. We assume we can figure out those details. Instead, we focus on the logical operations. Here's the Boolean logical counterpart to the previous electrical schematic. The NOT gate, like the other gates we will build in this video, have their own symbols as shown here. As we derive each of these gates, we may add them to our repertoire of tools that we can use to build up further logic. If we ever want to see the NAND gate circuitry at the base of our logic, we can recursively replace the higher level symbols with their derivations until only NAND gates remain. Next, let's build an AND gate from NAND and NOT gates. Again, you may want to pause the video here and see if you can figure out the logical schematic for the AND gate.
Sounds like a you problem.
This is also a very simple gate, and we can build its circuit using only half of the 7400 chip. Here's what the logical schematic looks like. And here's the schematic for the circuit. We see in the circuit that we can use two NAND gates of a single 7400 chip. The first gate performs the NAND operation, and the second gate performs the NOT function. We use the output from the first gate as both inputs to the second gate. Next is a gate that is perhaps a little trickier. It's the OR gate. As a reminder, here is the truth table for the OR Boolean function. Again, if you enjoy challenges, pause the video and take a minute to see if you can figure out how to construct an OR gate using only the gates we have already built. The secret to figuring out this one is to realize that the truth table for the OR looks a lot like an upside-down version of an AND. In other words, notice that the only place where an OR has a unique output is when both inputs are false. So the first step is to recognize when both inputs are false. Wanting both inputs to have some condition implies ANDing. And since we want both inputs to be false, we need to invert both inputs. What we are proposing is running each input through a NOT gate and then ANDing them together. However, the outputs from these three gates in this configuration would be just the opposite of what we want. That is, when both inputs are false, the output would be true, and every other output would be false. When our output is exactly opposite of what we want, it's easy to fix. All we need to do is invert the output with a NOT. So instead of ANDing the inverted inputs together, we want to NAND the inverted inputs together. Here's the logic schematic for the OR gate. Notice that we can build the circuit for this schematic with a single 7400 chip and still have an unused NAND gate.
The gate. The gate.
The final gate we want to build is the XOR gate. This is the most challenging of the gates. As a reminder, here's the XOR truth table. Again, if you enjoy a challenge, pause the video here and play around a little bit to see if you can figure out how to build this gate.
I always love a challenge.
As Boolean functions become more complicated, it becomes more difficult to figure out the logical schematic. One simplifying approach is to consider building schematics for individual outputs. We only need to consider those outputs that are true. If we can figure out how to build schematics for each of the true outputs, then we can OR these schematics to create the final result. Let's try this with the XOR table. If we could build a schematic that only outputs true if input A is true and input B is false, and if we can build a second schematic that outputs true only when input A is false and input B is true, then we can take these two outputs and OR them together to create the final schematic. Each of these two schematics is reasonably simple as shown here. Now let's OR these two schematics together to give us an XOR. Remember, an OR is a NAND with inverted inputs, so let's replace the OR gate. If we think about the implementation of this schematic, we realize it would require 9 NAND gates if we simply replace the Boolean gates with the definitions we previously constructed. Let's see if we can optimize this sum to reduce the number of NAND gates. We can represent the schematic as a Boolean expression made up of two sub-expressions. Note that when we write out Boolean expressions, the variables represent inputs. The plus sign means OR, and the dot means AND. The bar over a variable or expression means NOT. Let's take the left sub-expression first and refactor it. Notice that any Boolean expression, ORed with false, is equivalent to the original expression. Further, any Boolean variable and its NOT is equivalent to false. Therefore, any expression or a variable and not the same variable is equivalent to the original expression. That's a bit complicated, so let me repeat that. Any Boolean expression ORed with false is equivalent to the original expression. Any Boolean variable and its not is equivalent to false. Therefore, any expression or a variable and not the same variable is equivalent to the original expression. Based on these ideas, here's a way to represent the left sub-expression. Next, we can factor out the A variable. The final step is to apply De Morgan's law. De Morgan's law says that not A or not B is equivalent to the not of A and B. So let's apply De Morgan's law and rewrite the sub-expression like this. We can apply the same ideas to the right sub-expression to end up with this. Therefore, by substituting each of these sub-expressions back into the original expression, the entire XOR expression can be rewritten like this. When we draw the schematic for this expression, it looks like this. Notice the AND gates, where we then invert the outputs. We can rewrite these gates as NAND gates so that the schematic looks like this. Since this schematic is the schematic for an XOR circuit, it must be equivalent to the original XOR schematic, but notice that this schematic consists only of 4 NAND gates.
So I count to 4?
So we can build this circuit using a single 7400 chip. At this point, we have shown that we can create all the basic Boolean functions using only NAND gates. We have moved up 3 levels of abstraction, from basic electrical circuits to transistors, and finally, to Boolean logic gates. Chip designers also moved up the levels of abstraction. They have created chips that contain gates of each of the basic Boolean functions. Here are the numbers of the various chips. In the next video, we will work with these Boolean functions to move up one more level of abstraction. We will start to build higher-level binary functions from the Boolean logic. Then, in later videos, these higher-level functions will lay the groundwork for building an ALU, a CPU, and memory. Subscribe and click the notification bell so you can be notified of future videos.